So, okay, we will be recording this part of the session. If anybody has any objections with recording, please say so now. The previous session, we had started talking about the Routh-Hurwitz criteria. And so the Routh-Hurwitz criteria is a mathematical method, just to give a refresher there. It's a mathematical method that is comprised by what's called a Routh table, which is a special kind of tabulation, and the Hurwitz criteria, the Routh-Hurwitz criteria. Basically, the use of this method is to be able to identify if a system is stable or not. But more than that, it can also help us do design around stability for a certain parameter or value in the system. And we had already talked about that the first thing we do is to establish the Routh table. And basically, the Routh table is based upon the characteristic equation, which is the equation of the denominator of the transfer function of our system, where we're going to be getting the poles. Remember, and the poles give us information regarding stability. And so the first thing we do is do the Routh tabulation, where we establish the polynomial, different degrees of the polynomial, of the factors of the polynomial. We put them in rows, and then each column is going to be a coefficient, either if it's even or odd, of the characteristic equation. After that, we do a tabulation that's based on this, where the row where we're establishing the value is the pivot. So we do a negative determinant divided by the pivot value, which is the lower left-hand side value of the 4 that we're taking, and we fill in the table. Usually the table that we fill out is going to end up having a diagonal of zeros at some point. Lastly, once we do the tabulation, we're going to focus on the first column of values. And then the amount of sign changes that we have in the first column, from positive to negative or from negative to positive, the amount of those sign changes is going to tell us how many poles are on the right-hand side of the S-plane. And therefore, it's going to give us an indication of stability. And we had seen an example here where we had this closed loop system. We found the transfer function. We took the characteristic equation, which is the equation of the denominator. We did the Routh table and the Routh tabulation. Looked at the first column. In the case of this example, we've got 1, 2 sign changes from positive to negative and from negative to positive. That means that there are 2 poles on the right-hand side of the S-plane. That means that this system has poles on the right-hand side, which means that remember that if at least 1 pole is on the right-hand side, the system is going to be unstable. So this system is going to present some sort of instability. Now, there's a couple of special cases that occur in the tabulation that we're going to go through. So one of the first special cases is when we have a 0 in the first column. What do we do when we have a 0 in the first column? Now, this is important because if we have a 0 in any of the points of the tabulation here, if we've got a 0 in any of the first columns, then we can't continue the tabulation, because remember that in each of the steps, we're dividing by the pivot. And in this case, the pivot is always going to be the lower value of the first column. So we're going to be dividing by 0, and that's going to invalidate the rest of the values. So we can't do the tabulation if we have a 0 in the first column. So let's look at an example of how that can happen and what we can do. So we've got this transfer function. This is a complete transfer function. And we've got here our characteristic equation, which is the equation in the denominator. And so let's see how this Routh tabulation would look like. And I encourage you to please follow along in your notes. So the highest order is 5. So we're going to have s to the 5, s to the 4. Please be patient with my writing. This is an S, by the way, not a 5. S to the 3, S to the 2, S to the 1, and S to the 0. And for each of these, we're going to establish the coefficients that we've got here. So for the S to the 5, we've got a 1. That's the S to the 5. Then a 3. And then we've got another 5 here. We've got a 5, I'm sorry. 1, 3, and 5. Then the S to the 4 are going to be the next set of coefficients, which is going to be a 2, 6, and a 3. Now, if we do the tabulation for the first value, the value that's going to go here, I'm just going to do that one. It would be the negative determinant, or the determinant done the other way around. It would be 6 times 1 minus 2 times 3 divided by 2, negative. So 6 times 1 is 6. 2 times 3 is 6. 6 minus 6 is 0. Negative, it's negative 0 divided by 2. This value that we have here, this is going to be a 0. The value that we're going to have there is going to be a 0 once we do the calculation. And so the problem again with having a 0 here in the first column is that we can't continue the tabulation. So this first 0 that we have here stops everything. So what can we do? Well, what we're going to do is that we're going to substitute this 0. So instead of using a 0 here, what we're going to do is that we're going to substitute that 0 for a number that we are going to call epsilon. That we are going to say that this is a very, 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 very small number, a very small number that's very close to 0. So it's not 0, it's very close to 0. And we're going to substitute that here and continue the tabulation with that small value. By the way, you can use the epsilon, or you can actually put a value there. You can say 0.1, 0.01. It's good to use the epsilon because we're actually going to have to take 2 situations of epsilon. Epsilon is a very, very small value and it's positive, or epsilon is a very, very small value and it's negative. So we're going to substitute this value here for this very small value called epsilon. This very small value called epsilon. And we're going to continue the tabulation. Okay. So we're going to continue the tabulation. Now, to continue the tabulation, we would next take, well, we continue over here. We take these 2 values here. We take these 2 values here, and now we're going to combine them with these 2 for the second one. So it would be 3 times 1, 3. 2 times 5 is 10. 3 minus 10 is minus 7. Negative is 7 divided by 2. Then here we would have 7 halves. Oops. Here in this part here. And we haven't got any other values here, so this next one is going to be 0. Okay. And so on and so forth, we would continue the tabulation. Now, this is going to be kind of like those baking programs where we're looking at the ingredients and then suddenly we've got the whole cake already baked. So I'm going to jump over to the next slide. In the next slide, we've got the complete tabulation. Now, again, it's doing the same mathematical expressions that we mentioned before. And so we get the complete tabulation. And so in the first column, it's going to be in the function of epsilon. Okay, it's going to be in the function of epsilon. So instead of having a 0, we're going to have epsilon here. And the next thing that we're going to do here is that we're going to analyze two situations of epsilon. And I'm going to write them down here this way, and you guys can we can analyze. The only thing we're interested in is the sign, by the way. We're only interested in the sign. So we're going to take two situations here. We're going to say if epsilon is positive, I'm going to take another one here that if epsilon is negative. Okay, so first off, and I'm just going to divide this here up the middle. Okay. So help me out here. In the case of the first numbers here, regardless of epsilon, we've got a positive here and we've got a positive here. I'm going to go first with the epsilon positive. And here, if epsilon is a very small number and it's positive, then this is going to be positive. Now let's look at this one right here. Let's look at this one. Can somebody tell me if this expression is going to be positive or negative if epsilon is very small and positive? What's going to happen here?
It's going to be negative, right?
It's going to be negative. Let's see why. If you're correct, Marianne. Let's see why. Remember, these questions are funny, guys. You know why? Because they're binary, right? Marianne right now was right. And I know Marianne answered correctly because she knows the answer, okay? But it's a flip in the air. Is it going to be positive or negative? And you're like, okay, positive. Oh, you're correct. Or negative. No, you're not correct. So it's really a toying cost. But you're right, Marianne. It's going to be negative. Now let's see why. 6 times epsilon, and epsilon is a very, very, very small number that's positive. So 6 times epsilon, the first is that this number is going to be positive. But it's going to be it's epsilon that's a small number multiplied by 6. A small number multiplied by 6 is going to be smaller than 6. Minus 7, then the numerator is going to be negative. And since epsilon is a very small number that's positive, negative divided by positive, that means that this is going to be negative, correct? So Marianne was correct. Now this other big thing here, what's that one going to be? Marco, go ahead, shoot.
Positive.
Positive, I think so. Let's see. Epsilon is a very small number that's positive. And epsilon here is a very small number. So all of this is going to be, this 42 is going to be positive, but it's going to be smaller than 42. Then epsilon elevated to the square positive is still going to be positive, but it's going to be 6 times positive, which is smaller than 6. Okay, so something smaller than 42 minus something smaller than 6. And if I substitute negative 49, this means that this whole numerator is going to be negative. Okay, the whole numerator is going to be negative. Now here on the bottom, I've got 12 times epsilon. This is going to be positive and smaller than 12. Minus 14, the denominator is going to be negative. So this means that negative divided by negative is positive. And lastly, we've got the 3 that's positive. Okay, so if epsilon is positive, we're going to have that combination. Now let's look at the other side when epsilon is negative. Well, first off, this is positive. This is still positive. If epsilon is negative, then this is going to be negative. Now, 6 times a very small epsilon that's negative, this is going to be negative. And negative minus 7, all of this is going to be negative. Divided by epsilon that's negative, negative times negative, this means that this one is going to be positive. Okay. By the way, I don't know this actually. I don't know if you guys are gonna, I don't know if they let you use calculators in the Ceneval. I don't remember if they do or not. Because you're probably gonna have a normal Ceneval. You're probably gonna have a normal Ceneval next year. So I don't know if it's positive if they let you use calculators or not. But if you don't, then it's good to be able to do these kind of quick analysis without having to do with numbers. Over here, we've got 42 times epsilon. That's a negative number that's very small. This is going to be negative. Epsilon, which is negative, elevated to the square times 6, this is still going to be negative, or negative 6. Negative, negative, negative. Everything in the numerator is going to be negative. Then 12 times epsilon, which is a small negative number, times 12, this is going to be negative. Minus 14, then this whole denominator is going to be negative. Negative times negative is going to be positive. Oh,
Bless you.
thank you. Bless me. Thank you. And lastly, this number over here is positive. So what do we notice in both columns, which has to be congruent? Regardless of the value of epsilon, how many sign changes do we have? We've got 2, correct? I believe it was Diana. We've got 2, 1 and 2. And we've got 1 and 2. So that means that we've got 2 roots on the right-hand side, 2 roots on the right-hand side, and that would mean that this system has at least 1 root on the right-hand side. That means that it is an unstable system. Okay. Okay. So this is the second. This is the second case or the second special case that we're going to have. Okay. Okay. Questions with this one before we move on to the other special case. Okay.
No.
Okay. Thanks. Good. I'm going to clear this. We're going to go to the next special case. In the next. Oh, and this is this is the cake that's completed. This is the case that's completed. Where we've got the cake that's completed. I'm sorry, and we've got the calculations on the signs on the right hand side, same as we did on this example. So that's what we do if we get a special case when we got a 0 in the first column. Now there's another special case where the whole row turns to 0. It's different than just having the first 0 in the first column. If the whole row becomes 0, then even if we substitute an epsilon, we're not going to be able to do the rest of the calculations because the rest of the zeros are going to null everything. So let's see what happens. We've got a transfer function there. And so we're going to set up the Routh table here. So we've got an S5, an S4, an S3, an S2, an S1, and an S0. And so we're going to set up the Routh table here. So we, based on the characteristic equation, which is this one that we've got here, and we're going to take first the values like of the first row are going to be related to the S5, and they're going to be odd. So we've got 1, 6, and 8. And then we're going to have the second row is going to be the even numbers, where we were going to have a 7, 42, and 56. 7, 42, and 56. Now, in this case, remember that if we have a common factor, we can simplify. So here we've got 7, 42, and 56. We can actually substitute these for 1, 6, and 8. And notice what happens there. If we do that, we're dividing by 7 because it's a common factor. 168, 168. We've got exactly the same numbers in the first row and the second row. And what's going to happen there is that when we do the calculations, for example, we grab these two, we're going to have 7 times 6, 42, minus, I'm sorry, 1 times 6 minus 6 times 1, negative, divided by 1. This is going to be 0. And then when we try to do the same thing with the other pair, now we're going to grab this one and this one. And this is the pivot. We're going to have 1 times 8 minus 1 times 8 is 0, negative, divided by 1. This is 0 also. And the last column is 0 because we don't have any more columns. So the whole row has zeros. So we can't continue the tabulation. We're stuck. We can't put an epsilon here because even if we put an epsilon there, the rest of the tabulation is not going to work because of the rest of the zeros. So what we do here is that we're going to take what's called an auxiliary polynomial. We're going to grab this one here, and we're going to create a polynomial with this one. We're going to bring it over here. I'm going to bring that over here, and I'm going to create a polynomial, an auxiliary polynomial that I'm going to use to be able to do the rest of the tabulation. And I'm going to say that I'm going to create a new polynomial that's called P of S. And the polynomial is going to be the coefficient. So it's going to be S. It's going to be S to the 4 plus 6S to the 2 plus 8. By the way, I did the division by 7 just because it was a common factor and because it might simplify the calculations, but you could have also worked with the 7, the 42, and the 56. It's the same. And next up, what we're going to do is that we're going to calculate the derivative of P of S, of this auxiliary polynomial. Okay. And the derivative of P of S, reminding ourselves of our derivatives, it's going to be 4S to the 3 plus 12S. Okay. And what we're going to do is that we're going to grab these two coefficients. These coefficients that we've got here, and we are going to substitute them into we're going to substitute them into the row that was eliminated. So we're going to grab these two, and particularly the two coefficients, and we're going to substitute them here. So instead of having the 0 here, we're going to substitute it for the 4. And we're going to have a 12 here. And the 0 over here, we're still going to have it because there's no other factors there, but it doesn't matter anymore because now we can continue the tabulation with these new values. Okay. I'm going to jump over to the next slide that's got the solution here. It's got the complete tabulation. Yeah, so we've got the zeros here. We do the substitution. I substituted the 4 and the 12, but the 4 and the 12 also have a common factor, which is a 1 and a 3. So we can use that one. Those we can use the, again, we can use the 7, 42, and 56, and we can use the 4 and the 12, or the 1, 6, 8, and the 1, 3. It doesn't matter because it's just a factor that's being multiplied by everything. And we continue the tabulation using the same method. Now, what do we see in this tabulation here? How many sign changes do we have?
0.
We don't have correct, Marian. We don't have any sign changes in the first column because they're all they are all positive. So we're positive, 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 and positive. So there's no sign changes in the first column. Therefore, this system does not have any poles on the right-hand side, and therefore the system is stable. Okay. These are going to be the two special cases that we're going to have in the Routh's tabulation that we need to consider when we're doing the tabulation. Now, the Routh tabulation can be useful. All right, it could be useful like we've been seeing here. We've got a transfer function. We want to identify if it is stable or unstable system by looking at the amount of roots that are on the right-hand side. However, we already know that if we just grab the characteristic equation and find the poles, we're also going to be able to do that without having to do the tabulation. Okay, so think about that. Again, I can just grab the characteristic equation, put it in MATLAB, and ask for the poles and identify if there are poles with a positive real component, and that's going to tell me if the system is stable or not. So whereas the real use in the tabulation? Well, the real use in the tabulation is or can come related to stability design. So what does this mean? Remember that we're talking first of analysis of control systems, but now we're going to start to talk about design of control system. And design basically means establishing certain parameters for the system to behave the way we want. And the first thing that we want, or one of the first things we're looking for, is that the system be stable. The system be stable. So any other characteristic of the system, we need the system to be stable. So for that situation, for example, let's say that we have this transfer function and there's a parameter or a value k here, which again, this parameter k is the one that we can change or modify in the system. Right now, let's say that the k again is the controller. It's something that I can vary. However, and we saw that with the antenna system, and actually this was a question in the exam. In the antenna system, we've got the k, and if the system has a certain type of response, if I vary k, I know that the system is going to behave in a different way. Now, for this system in particular, we're going to need, we want to define the value of k, or at least know the values of k that are going to be allowed for the system to be stable. Because remember when we did the antenna system, we kind of gave values of k randomly, right? And the thing there was that depending on the values of k that we gave, the system was going to be stable or unstable, okay? And there was a point, there was a kind of a point where we kind of identified after these values or around these values, the system is going to be unstable. But it would be better to have a more precise calculation of that. So let's look at this example. We've got this transfer function with a parameter k, and we want to know the range of values of k that are going to make this system be stable. Before we select the ideal value of k, we first want to know the ranges of k for the system to be stable. And so what do we do there? Well, first off, let's find the transfer function, because right now we need the complete transfer function of the system, not the direct transfer function, which is what we have here. So we need to find that first, okay? So how do we do that? Well, we know that the T of S that I'm going to call, which is the complete transfer function of the system, which is the output divided by the input. Since this is a closed loop system, this is going to be G of S multiplied by 1 plus G of S multiplied by H of S. G of S is the forward transfer function. H of S is the feedback transfer function. And so we know that here, this right here is G of S. And what's the value of H of S, which is this one here? If we don't have a box there and we just have a line, it's what's called unity feedback. So this means that H of S in this case is going to be equal to 1. It's what's called a unity feedback system. It means that in the feedback, which is the measurement, I don't need to do any sort of processing of that. I directly take the signal and feedback. So in this case, H of S is going to be equal to 1. So we're only going to have G of S divided by 1 times G of S. And so therefore, for this system, T of S is going to be equal to G of S, which is K, divided by S plus 7. I'm patient with my writing. My arm really hurts. And S plus 11. And on the denominator, we're going to have 1 plus S times S plus 7 times S plus 11. Now we can multiply the whole expression by the denominator, S plus 7 plus S plus 11, and what we're going to have is T of S is equal to I'm going to do a couple of things here mathematically just to not write anymore. I'm going to be multiplying by the denominator. Okay. Oh, wait a minute. I made a mistake here. It's here it is G of S, it's K divided by S plus S multiplied, I'm sorry, by S plus 7 multiplied by S plus 11. Okay, so I'm going to multiply by that on each side. And I'm going to take advantage and also multiply this so we can have the whole polynomial. So S times S is going to be S squared multiplied by S is going to be S to the 3. 7S plus 11S, it's going to be 18S multiplied by S, it's going to be S squared. So it's going to be 18S squared. 7 times 11 is going to be 77 times S is going to be 77S. And plus k. And on the numerator, I'm going to have k. So now we've got the complete transfer function for the system. And this baby that we've got here on the bottom, this is going to be our characteristic equation. This is the one that's going to define the system behavior. And notice that this expression that's going to define the system behavior has a k in it. It has a parameter that, depending on the value of k, it's going to be the value of the roots of the poles in the end, and that's going to define the behavior of the system. Okay, so let's go to the next step where we're going to try to use the Routh criterion to establish values of k that are going to give us a range of stability. Okay, I'm going to jump over to the next slide. S to the 3 plus 18s squared plus 77. So let me say that. Okay, let's memorize that equation because I'm going to clear this. And so the characteristic equation that we had was, or is, s to the 3 plus 18s squared plus 77s plus k. And so we're going to do the Routh tabulation for that. So we're going to have s to the 3, s to the 2, s to the 1, and s to the 0. And so we're going to grab the values here from this equation. It's going to be 1. It's going to be 1 and 77 are going to be the values for associated to the first row. And then we're going to have 18 in k on the second row. And notice now that we're going to have a tabulation that depends on k. Okay. And so we're going to do the tabulation, and I'm going to switch over to the next slide that already has the tabulation. And so once we do the tabulation, we're going to have a tabulation that has k in it. So in the end, what we want is that we want the first column to not have any sign changes. Okay, we want the first column to not have any sign changes. So we notice that first off, we've got a positive number here. We've got a positive number here. And so for this system to be stable, I need a positive number here. That means that all of this has to be larger than 0. And that way I've just established a inequality. I also need this one to be positive. So this also has to be larger than 0. So I've established two inequalities that have to comply for this system to be stable. Okay, and so if I grab this one here, this inequality, and I solve it, I'm going to have, remember solving inequalities, 1386 minus k divided by 18 is going to be has to be larger than 0. Okay. Has to be larger than 0. We can just solve that inequality. The 18 is going to be eliminated, and we're going to have 1,386 minus k larger than 0. I can just send the k to the other side, and this would mean that for this one, k would have to be smaller than 1386. Combined with this other inequality, that says that k has to be larger than 0, then this means that for the system to be stable, we would need a value of k that was between 0 and 1386. As long as our k is within that range, the system is going to be stable. Some sort of stability. Right now, we haven't selected what is the best value of k for this system. That would depend on the parameters, the design parameters. We'll see how to do that further on. But right now, at least we know that the range of k has to be within that value. It can't be larger than that value, okay? Because if it is, then the system is going to present some sort of instability. Okay. And so this way, the Routh-Hurwitz criterion can help us identify or design around stability for a system. Okay. Questions up to this point before we move on?
No.
Okay. Good. Thanks. Okay. Now let's look at this example. Remember that we had already started playing around with the antenna. Remember that we'd already started playing around in MATLAB with the possible values of k. But what we want is we want to know the exact values of k for the system to be stable. Okay, for the system to be stable. Okay, and so what we want here is to find the ranges of values that generate a stable or marginally stable or unstable response for the closed loop system. And so the first thing we need to do is to find the values of k that are going to generate stability. And we can do that with the Routh-Hurwitz criteria. Okay, now I'm going to give you a few minutes to try to do this on your own. And then we're going to try to solve it here together. Okay. Remember that what we need, first off, we need the complete transfer function for the whole system. And we had already found that previously in unit 2. We need the full transfer function. From that, we're going to get the characteristic equation. Okay. So I'm going to give you guys a few minutes to try to do that, and then we're going to solve it here together. Okay, so let's see how we can approach this. Okay, so first off, we've got the system here. Oh, by the way, this exercise that we're going to be doing right now, we're going to be focusing on configuration 1, which is the one that we have already. We already have the block diagram parameters for. You had already calculated, or you've already done in lab exercise 1. You'd already done the calculations for configurations 2 and 3, and actually lab 2 is gonna be related. You're gonna be doing some exercises with regards to this. So first off, we're going to be using, or we're going to be needing, the complete transfer function of the whole system. And remember that we had already found that. Okay, we had already done that previously in the last unit. We had already found the complete transfer function for the system, which was this one. Okay, we had already found the expression that related all of the parameters of the whole system, and we'd already done that procedure. So this is going to be the transfer function we need to evaluate the stability and using the Routh-Hurwitz criterion. So we're going to grab this transfer function. We're going to grab this transfer function, and from that transfer function, the one that we're interested in the end, or the one that or the part of the transfer function that we're interested in, or we're going to be working with, is the characteristic equation, which is this equation here on the bottom, okay? Which is this one that we've got here. I'm going to remember, let's just remember that that this part here, we need to actually multiply this. So this is going to be actually s to the s times s is going to be s squared. So this is going to be s to the 3. As times ams is going to be plus a plus am multiplied by s, but it's going to be also times s. So this is going to be s squared. And lastly, a times am is going to be am multiplied by s is going to be am. Write that down a little bit better. Please be patient. A times am s and the whole other bunch of k's we've got here. K, I'm just going to put that with a different color just to remember that k is the parameter that we're going to be varying. It'll be k times that whole other bunch of k's that we've got there, which is k1, km, kg, and k pot. So this is going to be the expression that we are going to be, this is going to be the expression that we're going to be using, okay? It's the expression that we're going to be using to do the Routh-Hurwitz calculations, okay? Let me paste it over here. Okay, give me a moment. One moment, I'm going to paste that equation because it's the one we're going to be using. And I'm going to need the help. I'm going to need you guys to please help me out with the calculations of the parameters so we can complete the values of that equation. So I'm going to need you guys to please help me out with those values, okay? Give me a moment just to copy paste it here. Okay. And okay, good. Okay. Now that I've copy pasted it on the other slide, now let's fill in those parameters. Okay. So we've got, let me clear this. So we've got this equation here. Help me out with the calculations here, please. If you would be so kind, I would really, really appreciate it. So this would be s to the 3. How much is a plus am? You've got the values there. Somebody please help me out with that value. A plus am.
101.71 is squared.
101.71 s squared. Thank you very much, Marianne. Please, everybody else, please verify. What is a times am? If somebody could please help me out with
171.
171. Thank you, Daniel. Does it have any decimals? Just so.
No.
No, 171 s, perfect. And lastly, how much is all of this bunch of k's multiplied? K1 times km times ka times k pot. Can somebody give me that?
6.624.
6.624. Okay, good. And that's going to be multiplied by k, which is the k that we don't know the value. Okay, good. Now we need to do we're going to need to do the Routh tabulation. Okay, so give me a moment to do a quick copy paste here. A moment. It's a good thing about using Zoom, and we can take quick screenshots here that are really, really useful. There we go. Okay, good. Okay, so now that we've got our characteristic equation, okay. Okay, now that we've got our characteristic equation, we can continue to do the Routh-Hurwitz tabulation. We're going to go to the next slide here. Now that we've got the characteristic equation there, we can do the tabulation. And so we're going to come over here, and I'm going to need your help also with the tabulation. So we've got s to the 3. We've got s squared, s to the 1, and s to the 0. And we're going to grab the values here from the expression. So the s to the 3, which is the first row, we're going to have a 1, a 171. Yeah, the 1 and the 171. So we're going to have a 1 here and a 171. And for the second row, we're going to grab this one and we're going to grab this one. It's going to be a 101.71 and the 6.6. I'm going to leave 2 decimals. Well, let's leave the 3 because we wrote them down. 2 would have been fine, I think. 6.624. And we got our value of k here. Okay. It's important, actually, I'm going to mention this now. It's going to be recorded so you guys can remember. Some calculations that we're going to be doing with control systems methods and some examples and stuff that we're going to be doing using some methods there are actually going to be sensitive to they're actually going to be sensitive to the decimals, which is kind of unfortunate, but it's true. They are going to be sensitive to decimals. So just be careful with that when you're doing some of the calculations, because some of them are going to be sensible to decimals. Okay, so particularly when we're going to be working with the root locus and a few of the other ones. But for now, let's leave the 6.624. Now, please help me out with the calculations. It's actually just two calculations that you need to do. Why? Because we know that this is going to be 0. So we actually just need the number that's going to go here, not number, the value, because we're going to have k, and the one that's going to go here. So let's see. Can somebody help me out with that? I think somebody had raised their hand. Carlos, go ahead, please.
Yes, I have it. It's
Thank you.
170.93.
Okay, let me write that down.
But there's, yes, that one. There's more decimals. I don't know if you.
Just let's use 2 for now.
Okay.
Let's use 2. So again, could you repeat that, please?
It's 170.93.
Okay, but where's the k?
Oh, okay. Yes, I'm sorry.
Yeah, so remember that we're doing the matrix, but we have to include, this factor here has the K in it, okay? So we have to do
Yes.
it with the K, okay? Okay, so doing the calculations with the K, can somebody tell me what we would have here in this one, please?
It's gonna be the whole thing with the, it's not gonna be a single number, but
I know.
like the entire
Mhm.
fraction.
Yes.
So it's, I mean, it's 6 point, it's the same 6.624K minus
6.624 K.
minus 17392. It's like a
Okay.
big number. It's
Give me a moment here. I'm going to erase this just to have a little bit more space. 6.624K minus, could you say that again, please?
17392.
17392.
0.41.
0.41. Please, the rest of you verify that. And that would be divided by 101.71, right?
Yeah. So because that's the multiplication, right? Like between 101.7, like the right number, the big number. That should be the
But I
multiple.
think that
The
the
signs.
signs are incorrect. It's
Yeah.
minus 6 and plus.
Yeah.
7
Remember
plus-
that we're calculating the determinant, and it's the negative determinant.
Oh, it's
Okay?
minus.
Yeah. And so if it's the negative determinant, then this would be, like Diana mentioned, I believe, this would be minus and this would be plus, and still divided by this. Okay. Could somebody, thank you, Diana, and thank you, Daniel, also. Could a couple of more people verify these calculations and that expression that we have there is correct?
It is. I just checked it on MATLAB.
Okay, good, good. Okay, and what value have we got here on the bottom? That's going to be that should be an easy one. So remember that we're grabbing these two. Okay, so it's going to be 0 times this number, which is going to be 0. This minus this times this divided by this. And so actually what we're going to have here in the bottom is what? It's just going to be 6.6. 6.624K. Okay. And actually, this last one that we get in the column, it's just, notice something interesting. It's just to validate that K is larger than 0 for these cases. So K has to be a positive number because of our configuration system. Okay, remember that we're talking about a gain, so we're not considering a negative gain. And so once we have this, now we look at the columns and we observe that the first column is positive. The second row, I'm sorry, is positive. That means that these two also have to be positive and positive. That means that the inequality that we're left with is that, just write this down here. This is 0, goes over here. It's a second column. That means that this has to be larger than 0. And this also has to be larger than 0. Okay. If we solve this inequality, can somebody please solve this inequality? What value of K do we get? K should be less than?
It's a negative number if you solve for K.
No,
Is it supposed to be?
no, because it's
Positive.
it's negative divided by negative. So to solve this inequality, the 101.71 is going to go to the other side. So this one is eliminated. And it's going to be minus 6.624K plus this large number. We're going to send that to the other side, or send the 6.624 to the other side. So we're both are going to be positive. So it's going to be 17,392.41 divided by 6.624. K should be less than that number. Does somebody have that calculation, please?
$2,625.
2,635.
25.
2,625. Okay.
0.66.
Okay, I'm gonna round it up. So can somebody please, thank you, Daniel. Can somebody please verify that value?
Yes,
Is that
I
one?
give you that.
Good. So K should be less than, could you repeat the number again? 2625?
Yes.
2625 point, let's give me 2 decimals more. Point how much?
66.
66. Okay. And combined with this, combined with the larger than 0, then this would mean that K would have to be within this. K would have to be within that range for the system to be stable. That's assuming that we didn't make any mistakes with calculations. Okay. Assuming we didn't make any mistakes with the calculations, then the range of K for stability should be within this range that we have here. Okay. Now, depending on what we want specifically the antenna to do is what values we're going to specifically take for K. Okay. But for now, we at least know that the range of stability is going to be within those values. Okay. And that's how we can use the Routh-Hurwitz criteria to be able to find or at least identify ranges of values for the parameter we're looking at to be able to identify stability.